So this guy is world champion in juggling. What he can do, only a few people can do. But everybody can do something simple like this. That works for everything. Biology, chemistry, physics. You don't need to be Einstein, yeah, but everybody can learn elementary physics. It requires only practicing, and that practice includes visualization and drawing pictures. And 1, 2, 3, 4, so 4 pages of pictures. I recommend, I will upload it to the Blackboard. I recommend find yours and look at the pictures drawn by other people. See, compare. What is a good picture? Well, first of all, a good picture is a large picture. A good picture, when you do a homework, should have a space like a quarter of a page at least. Yeah. Now, what is a good picture? A good picture when a straight line is a straight line, when a right angle is a right angle. So, but that's geometry. Also, there's some physics. A good picture when forces which are supposed to point in a way they're supposed to point in a way they're supposed to point. Yeah. For example, gravity always has to point down, and normal has to be perpendicular. And here, for example, every arrow should mean something. Where is it? Where is it? Where is it? I saw a couple of things which I want to mention. Well, before I move on to the next slide, this is absolutely right, but it's kind of overkill, you know. Sometimes we have to use the minimum necessary information, like here or here. When we draw the same object at 2 different locations, it's actually easier and more convenient using the same picture, not 2 different pictures, because especially when we need to see displacement. That's just supposed to be a part of the same picture. Here, yeah. Gravity doesn't oppose normal force. It's also a very common situation I've seen before. Gravity always points down. That's it. Here, I don't know why, but the person, by some reason, changed the direction of the forces. You know, if you choose the direction of the force, stick to this until you solve the problem. Don't change anything during the process of solution. Be consistent, even if it's wrong. Being consistently wrong, better than being inconsistent in physics and in life. Well, so check different, see, many very nice pictures, yeah, but some pictures are really strange. And again, visualizing things, it's not an ability which comes from genetics, it's a skill. It just requires practicing. That's it. Now, this is what we've talked about. Can you hear me? I don't hear myself, so I'm not sure if the sound is fine. Okay, thank you. Impulse momentum theorem. We said that this equation we can apply to anything. Yes, anything means, bless you, a system. A system might have many parts, a system might have a few parts, we're going to concentrate on a system which has only two parts. Two parts, like two cards. And when something like that is happening, we call it a collision. The interaction time is very, very short. That's why the interaction time is very, very short. That's why we can assume that the total momentum of a system remains the same. But if a system has parts, what is the total momentum equal to? Well, the answer is, of course, it should be equal to the sum of the individual momentum of each part of the system. I'm not sure what was the range of this radio. I hope you've heard what I said. So, different type of collisions you will study in the lab next week, and we're going to talk about today. This is one of the types of a collision when two objects stick to each other. They form one new body, and that body, that object, travels as a whole. But still, we can treat each individually before and even after this type of a collision, when they traveled separately before the collision and keep traveling separately after the collision. And also, depending on what's happening to the energy, we can introduce 4 different types of the collision. But for every possible type of a collision, if we have two objects, the linear momentum of a system always is equal to the sum of a linear momentum of this plus this. We just need to remember that a momentum, a p with an arrow, is a vector, which means every time we need to draw a picture which represents each object traveling. And in this equation, each variable has a very specific meaning, and we need to be able to say it out loud. What's this? This is a linear momentum of the first object. Well, F usually means final, and final in this situation means after the collision had happened. And this is a linear momentum of another part, second card, after the collision. And this is a linear momentum of the first object. Initial means before the collision. And this is a linear momentum of the second object, again, before the collision. But since a collision happening very quickly, plus because of the Newton's third law, internal forces don't affect the momentum of a system, this sum remains constant. So if we take two instances, one before collision, second after collision, if we calculate this before, if we calculate total momentum after, they must be equal to each other. This is the law, and we call it a law of conservation of linear momentum. That's it. Or LCLM. Now, definitions. Yeah, we need to know the names. The easiest one is this one. Absolutely inelastic collision. This is a type of a collision when they travel after the collision together, yeah, like this. Absolutely inelastic. So they form one object. Now, inelastic collision, that's basically any normal collision. They collide, they move, but because they touch each other, there might be some friction happening between, and friction always decreases kinetic energy. So there is some work done by friction. And in general, we don't have an equation for calculating work when something like that happening. So in general, we just know it's there, but how much of work has been done, we cannot figure out until we actually solve the whole problem. We can calculate energy before the collision, we can calculate energy after the collision, and that difference will be that amount of work done by friction during the collision. Now, elastic collision, but outdated and preferred name is absolutely elastic collision to counter absolutely inelastic collision, is a collision when we neglect the work done by friction. We assume that the collision was ideal and that energy, kinetic energy before and after the collision was the same. So this is what is really happening, and this is an ideal case, imaginary case, when we set this to be equal to 0. We neglect friction. And superelastic collision, when something like this is happening. So it's like an explosion. Energy after the collision actually is greater than it was before. So these are just names. And of course, the easiest collision, well, in the lab and here, except one problem, we're going to talk about one-dimensional situations only. So for the one-dimensional situation, we choose the x-axis, and in that situation, each variable has a certain component. If we know that a vector points to the right, we know the component should be positive for that vector. If we know that a vector points to the left, we know that the component should be negative. So here, again, every variable represents a very specific velocity. This is the velocity of the first object before the collision relative to x-axis. That's it. And in this situation, if I refer like this object to be number 1, the velocity before collision points to the right, so that's supposed to be some positive number. That's it. Sometimes we don't know, especially if collision happening, and depending on the situation, the result is different. This car, after the collision, might keep traveling to the left or might start traveling to the right. We don't know. In general, until we solve a problem, we don't know what will be happening. So what do? We just assume that after the collision, they all travel to the right. We assume it's easier. And then we solve. And if the final number is positive, our assumption was correct. If the final number for the velocity turns out to be negative, it means our assumption was wrong. And in reality, after the collision, this car will be traveling to the left. That's it. So when we know a direction, and normally we know directions before the collision happening, we write actual values plus for moving to the right, and minus negative for moving to the left. What's happening after the collision? We solve it for that. Okay, so this is a situation. Takes years of practice. Okay, you can watch one more time. The question is about kinetic energy. We know that energy, just energy, is always conserved. It just might be transferred from one form into another form. But in this particular collision, what should you say about kinetic energy of the system? Is it the same before and after? Does it change? Is energy conserved? Or maybe we need more information? Again, a new toy. If you have a toy, you have to play with it. So what do you say?
Said yes.
Yes means conserved.
Yeah.
And do you have any type of reasoning to support?
I figured because their mass was about double what their mass was, the sum of the two parts, that makes up for their lack of velocity.
So every time when we need to analyze a collision, any kind of a collision, we should divide the universe into two parts, before and after. Before. Did they move before they collide? Yes. The cart on the left was traveling to the right. The cart on the right was traveling to the left. After. Did they move after the collision? Barely. So, after the collision, they practically were resting. Any questions about what we saw? Because this is just an illustration of what we saw with our own eyes, right? How do we calculate kinetic energy? Yeah. So mv1 squared over 2 plus mv2 v2 squared over 2, that is a kinetic energy before the collision. That's what we call initial, or first, or before. And after the collision, that should be m1 plus m2 times speed squared over 2. So traveling, not moving. This is a positive number, this is a positive number, that is definitely some kind of a positive number. This is practically 0, that makes this is practically 0. So if energy was not 0 and now it is 0, is it conserved?
No, but why don't you factor in the fact that you have two objects moving in two different directions?
That's, I don't understand. I have added the energies of two objects traveling in different directions. V squared, that's velocity squared. If you square anything, it just gives you a positive number. If you want to calculate the energy, you just calculate the energy of each part. Does it have kinetic energy? Does it have kinetic energy? Does it have kinetic energy? That's it. So, was it conserved? Yes?
So I thought that mechanical and kinetic energy were different. I'm just confused because the question was asking mechanical and then they just did.
That's a very good question. But in this particular situation, and in all situations in the future, mechanical energy and kinetic energy will be equal to each other because of what do you think? Why? Yes, there's no height. This is assumed, kind of, yeah. Potential energy, theoretically, is a part of mechanical energy, theoretically. But if potential energy is zero, mechanical energy is kinetic energy. Good eye. So, if we would want to write the law of conservation of mechanical energy for this situation, and we will, but we would have to write what's this? This room has ghosts. So the law of conservation of mechanical energy in general, mechanical energy initial plus the work done by friction. Friction equals mechanical energy final. So kinetic energy initial plus potential energy initial plus work done by friction equals kinetic energy final plus potential energy final. Now, when everything is happening on the ground, we don't have this term. mg0 equals 0. So only kinetic energy matters. That's why when we talk about collisions, we use terms mechanical and kinetic interchangeably. You know, it's the same thing. Kinetic energy final. And this is how we can calculate the amount of work done. The amount of work done by force of friction should be equal to this difference, kinetic energy final minus kinetic energy initial. In our specific experiment, that should be equal to 0 minus which is negative, of course, because friction always does negative work. This is a generic example, and we're going to solve a specific example very soon. So, this picture actually tells us initial velocities and masses. So let's just solve this problem. You need to transfer the picture first, because I already have it. Yeah. So you should have your own picture. To this picture, I only need to add one element, the axis. This should be called, well, if this is a number 1 object, this is a number 2 object, this should be called the velocity of the first object before the collision, or initial. This arrow should be called the velocity of the second object before the collision. And technically, this should be called M1. That should be called M2, V1, V2. And of course, we assume international system of units. So kilograms, meters per second, kilograms, meters per second. And technically, in this specific case, we could predict what should be happening, because one is heavy and fast, second is light and slow. But again, we don't have to. The picture you see is the picture we call before the collision. Now we need to draw a picture which represents what's happening after the collision. We don't care about during. So after theoretically, we have only two choices for the after. They travel together or separately. The third choice doesn't exist. How do we know? We have to read. Sometimes it's in the name, sometimes it's in the description. Absolutely inelastic, according to a definition from the previous slide, it means they travel together. That's what it means. So that's why names are important. Absolutely inelastic means after the collision, they travel together. How do they travel? Well, we can assume to the right, and it will be to the right, but it doesn't matter. Now, since they travel together, we don't have to now invent two different velocities. It's the same velocity. It's one velocity. We can just write a letter v. Well, final or after. Also, very often in textbooks, people use v's, v and v and v and v for velocity before, but for velocity after, they use a u, just to separate. Doesn't really matter. I like u's. And now we are ready to apply the law. This is, again, a generic expression, but it has to be written twice, before and after, and the law says those two expressions must be equal to each other. For before, what should you write? M1 times V1 initial x plus M2 times V2 initial x. That's it. What should we write for the after? They travel together, so the new object has just a common combined mass times V final x. Now we need to use numbers. Nothing else left to do. So 2 times, every time when we write a component of velocity, we have to ask the same question, is it positive or negative? And the answer is in the picture, right? So the magnitude of this velocity is 2. What number should I write? A 2 or a negative 2? 2, because it points to the right. Plus 0.4 times, what number should I write here? Negative 1. If you don't account for the direction, you may make a mistake. That's it. That's the most important part, looking at directions. Here, well, theoretically we don't know. Theoretically, this arrow represents our expectation, which might be wrong, but we should write 2 plus 0.4 times this. And this number, again, theoretically, can be positive or negative or even 0. Wherever it is, that's the answer. So that's what we need to solve for. Will be equal to 4. I forgot. I think on Thursdays I write correct 4s. 4 minus 0.4 divided by 2.4 equals 1.5, I think. A positive number, which means they do travel together to the right. And that's how fast they're going to travel. And this strategy works every time. Yeah, 1.5. Did the energy change? Yes, we know it did. How much did it change? Well, all we have to do is just apply that very equation. Kinetic energy initial should be equal to 2 times 2 squared over 2 plus 0.4 times 1 squared over 2. You know what? Let's write 2's and 4's today. And kinetic energy final, but should be equal to how do they travel together? So total mass. How fast do they travel together? We just found that speed, 1.5. Yeah, but I don't guarantee 5s over 2. These are two numbers we need to compare. The work done by friction will be equal to difference final kinetic energy of a system. I don't write it specifically, but we need to keep in mind we talk about a system which has two parts, two cards, minus kinetic initial of the system. And calculation tells negative 1.5 joules, the difference between those two. It has to be negative. It might be positive only for a super elastic collision, when something made a move away from here, like a spring or an explosion, when we're adding energy into the system. Any questions? I think it's very straightforward. So there are many situations when we can talk about similar mathematics, yeah? But sometimes we should use our imagination. So if we look at this experiment we recorded, we had two separate objects, and after, only one. But now if we watch that record backwards, what would we see? We would see one object traveling, and then it separates in two different objects. So does it really matter how we look at it one way or another? No, of course not. It's just initial and final kind of switched, but mathematics completely the same. Physics is completely the same. So when an explosion happens, or someone walks and jumps off, we can apply exactly the same type of reasoning. Absolutely, no difference at all. And if you remember, we had a cart with a fan. When the fan works, the cart is moving. Why? Well, Newton's third law says if the fan is acting on air, the air is acting on the fan, and that's why they move. However, in order to move, that cart needs air. So, for example, we cannot use this principle to travel into outer space because there is no air outside. So what do? Well, we use a different principle. The same law, Newton's third law, says that if two objects separate from each other, they should travel in opposite directions. Like this. Or something a little bit more straightforward, a rocket. This is a standard, actually, yeah, standard CO2 cartridge. It has compressed CO2 gas in it, and compressed, really compressed. So if I pinch it, it makes this move. Why do I need this? Because without this, actually this thing becomes dangerous like a bullet. We did it before. It flies around. People might get hit. So that's why we need something heavy, so it would travel slowly. But now imagine same principle, different direction. Yeah. That's how we conquer the outer space. Newton's third law. This device doesn't need the air. Yeah. And if you shoot recoil, Newton's third law. So all our space exploration is based on this principle. And how do we calculate the velocity? Well, if it starts from rest, the initial velocity of the system is 0, right? And then they start moving. So we can figure out the way how to measure the velocity of those gases, and we can use it to calculate the velocity of this part, the solid part. It's been done first time by actually a Russian school teacher. You can Google. All right. Next specific example. Please read it and try to solve it. I'm going to stop talking for maybe a minute. Please read carefully what's happening. The strategy says you should draw a picture representing two objects before the collision, and then you should draw a picture representing the same objects after the collision. The information is here in the numbers, in the words. The most important picture here is, of course, after, because you have to imagine what's happening after. You don't have to imagine what is happening before because you see it, right? But that next part requires imagination, visualization, drawing as accurate as possible. When straight lines are straight, when directions to the right point to the right, and directions to the left point to the left. Piece of paper, pen. If you're watching slides, listening to a professor talking, it might make you feel like you learned, but as you know now, don't trust your feelings, right? It's a very common misconception that people learn by watching and listening. No, people don't learn by watching and listening. So here we have two objects. We call them one and another, left and right. And they're supposed to be, the equation, the law, has 4 velocities. 2 before and 2 after. So we need to know 3 to calculate the 4th. Otherwise, it wouldn't be possible. Which velocity will be unknown? Final velocity of which card? Of 2 kilo. Yep, exactly. That's it. As long as we said that, the rest is absolutely clear. All right. Absolutely clear. We just, so before, do you really need wheels on my picture? Not really. Okay, so 2 and 2. and 0.4 and 1 are same cards. And after they travel separately again. So two objects, but this one now travels to the right. The magnitude is the same. How do we know? We read and give a correct interpretation to what we read. That's it. So this is what's left unknown. And again, every time when we don't really know how it's going to travel, we assume it travels to the right. And then we see what's happening. So in this situation now, it's very easy to write an equation. M1, actually, okay, one more time. On the exam, I wouldn't even write an equation. On the exam, to save time, I would start writing numbers immediately. But here, bless you. And I call them U before, V before and U after. So 2 times 2 plus 0.4 times -1 should be equal to 2 times. And when I write numbers, actually, I don't need any subscripts anymore. That's the only letter in my equation left. Plus 0.4 times 1. That's it. So this is again 4 minus 0.4. Now I have to subtract 0.4 again, divided by 2. That gives me my unknown. For 3.6, 3.2, 1.6. The most important piece of information here, it's positive. So it does travel in the same direction. So it doesn't bounce back. And we saw that it might be happening. You know, we kind of assumed that when objects collide, they must bounce off each other. That's what we used to call collision bouncing, but not always. Yeah. Sometimes it keeps traveling in the same direction. It depends on mass difference, mass distribution, and speed distribution. I could do something differently, like this. So that's why I always say, until we solve the problem, we don't know what's going to happen. We have to solve the problem and look at the final numbers. That's it. All right. Well, energy. Energy, again, very quickly, we just have to compare two numbers. I'm not going to, so there is kinetic energy initial, 2 times 2 squared, actually the same as before, plus 0.4 times 1 squared over 2. And there is a kinetic energy final, which is 2 times now 1.6 squared over 2 plus 0.4 times 1 squared over 2. Masses are the same. Second card on the right has the same speed as before. It was 1 meter per second, now it's 1 meter per second. But the first card changes, so we can actually see decreases energy. Yeah. It was 2 squared, now it's 1.6 squared. So we just solved this. Now, general case of absolutely elastic collision. So people nowadays people do not say this word absolutely. They mean it. But I actually love call it complete name, absolutely inelastic, because this word absolutely tells me that there is no friction between cards. We neglect any friction, which means mechanical energy remains the same before and after, which means kinetic energy of the system remains the same before and after. That's what it means.
How did you decide that this problem was absolutely elastic?
I don't decide anything. I read whatever slide.
I didn't know the problem.
The previous, no, it wasn't.
Okay, what was that?
I just compared these numbers. Initial actually is greater than final kinetic energy.
So, like on the slide before, it had at the top inelastic or super.
Well, this is inelastic. Yeah. Superelastic would mean that the final energy is greater than initial. Yes. And if energy would be the same, that would have been absolutely elastic or elastic collision. So the name of a collision is related to what is happening to the energy. So, and in general, energy is supposed to change because of the internal friction. But if we neglect, we actually can apply a second law in addition to the law of conservation of linear momentum. We can write the law of conservation of mechanical energy with no friction. And now we have two equations. If we have two equations, that means in mathematics we can solve for two unknowns. And this is a purely mathematical thing. So I'm going to do it once. In general, these are velocities before the collision. These are velocities after the collision. Here, the collision happened. Now, we write M1V1 plus M2V2 should be equal to M1U1 plus M2U2. But in my mind, I know that V1 actually represents the X component. I'm lazy. I don't want to write X, 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 X 4 times. V2 represents X component. U1 represents X component. It would be consistent. So there are some things which I keep in mind and don't write every time. But now we can add another equation. The problem with the second equation is quadratic. Technically, not a big problem. We can always use a quadratic formula if we want to. But there is a way around it. Every textbook has it. And the way around it is algebraical, pure algebra. First step, I collect all terms related to one object on the left and all terms related to another object on the right. Then I can see that mass m in both situations becomes a common factor. So I use algebra, and here there's an equation which belongs probably 8th grade algebra. It's called difference of squares, or difference between two squares. And you don't have to do that. Yeah. All we need to know is the result. This algebra tells us that for absolutely elastic collision, in addition to this law, in addition to that law, we could also use this equation with just a mathematical consequence of those two. But now it's much easier, has no squares in it. So instead of using complicated quadratic equation, we can use this simple equation. We can. It's on the equation sheet if we need it. So that helps. That helps us to solve problems without going through that algebra again and again, which you could, without solving quadratic equations again and again, which you could. Just a second. I have to take this. Yes.
Oh, hi, Valentine. It's Gail with Atrius. I have your wife here.
Yes.
Hi, I'm just verifying you're going to be her ride home.
Yes.
Okay, so just protocol. I know you're teaching, you can't answer your phone, but the protocol is when she gets into recovery, the nurse will automatically call you and leave you a voicemail.
Yes.
Okay, and we know you'll be here at 1 o'clock?
Yes.
Okay, we'll see you then.
Yes.
Thanks. Bye.
So, what? If every conversation would have been like that, life would have been much easier. So, you see, this equation, the law of conservation of linear momentum, remains well, applied again and again for any collision. But this is what we use instead of law of conservation of mechanical energy. So numbers. 2 times 2 plus 2 times 0, that's what we know, should be equal to. Well, we actually don't know. All we know is that after the collision, we will have again two objects. They will be traveling. Do we know how? No, we don't. So we assume they travel to the right. And, well, all we can write is just 2 times this should be equal to 2 times this. That's the law of conservation of linear momentum. And what should we write here? That's the initial velocity of the first cart, 2, plus. What does it represent? The final velocity of the first cart. Do we know it? No. So what do? Do we keep this space empty? Of course not. If we know a number, we write a number. If we don't know a number, what do we write? The variable which represents this number. Same here. Now we need to solve it. So first of all, I just cancel 2, 2, that's 0. So 2 equals this plus this. On another hand, 2 plus this equals this. How do we solve equations? Well, we have various approaches. We can use substitution. We can use addition. Let's use substitution because I already have an expression for second velocity. I can just use that expression. This action has a name, substitution or simply replacing. We replace a variable with the expression it's equal to. What does it say? Please tell me a number. 0. What does it mean? What does it mean? Yep, after the collision, it stops moving. What about this cart which was at rest? what velocity will be? Okay. So that's 0. U2 equals 2 plus 0. Why did you say negative 2? So what does it mean? Well, something like this with same masses. One is at rest, second hits it. Oh. The grooves, well, just a little bit slower. Stops, travels. Do you play pool? Do you do this? That's what you do when you want the cue ball stop. You have to hit straight, hard. It stops. Yes?
And this is absolutely elastic.
Yes, because it's based on the use of this equation, which assumes that there is no friction. Otherwise, we would have to use an additional theorem, W, and that would change everything, because normally we don't actually know W. This word means no work done by friction. All right, ballistic pendulum. This is this thing. A device like that originally has been used to measure how fast a bullet travels when it's shot from a rifle. So this is what we call a pendulum. It swings back and forth. And in this device, if you hit it, it actually stops moving at a fixed location. You can measure this angle, and if you know all other stuff, you can actually calculate how fast it was traveling initially, and we will do something like that. So, well, first of all, this is a spring gun, similar to you used in the lab. There is a spring, so when you compress the spring, you do work by your own hand. And the spring stores some energy. It's called elastic potential energy. We're going to talk about it later. And now if you release it, that's it. And again, we can use this to measure how fast it was traveling initially. Our goal is to calculate that height. And the question is, don't answer the question yet. You don't know what it's about. First, I have to give you something to think about, and that's what I want to do. So this bullet flies at 100 meters per second. So clearly, it has a certain kinetic energy, mv squared over 2. And when the pendulum stops here, this pendulum doesn't have kinetic energy anymore. Yes? But now what energy does it have? Gravitational potential energy, which is mgh. Well, the mass, of course, should be total, because that box holds the bullet in it, so it should be m plus m times g times h. And the law of conservation of mechanical energy tells us mv squared over 2 should be equal to m plus m gh. So we can calculate the height should be equal to, well, in numbers, grams 0.01, speed 100 squared divided by 2. 990 plus 10. That's 1,000 grams, which is 1 kilogram. And G is equal to 10. So 5? Five. Now, you can enter your answer to this question. Is this solution correct? Yes, it is correct. You choose 1. No, it's wrong. You choose 2. So by now, I'm absolutely positive you know what you want to answer, so I can switch to the website to check. Hmm? I didn't get the question. What the question? Okay. 1827. So, what did you say? If you think it's you, you know the rule.
I said no.
If you said no, you have to have a reason for that, because if you have no reason to say no, you have to say yes.
I said no because unless I plugged in the values incorrectly, I got the right side to be, I believe it was, and then the left side to be. I might have done my math wrong.
Mathematics might be a reason, I agree. But I wouldn't stick to mathematics here. I would think about physics. What did you say? Yes or no?
I said yes, but I'm not sure.
Okay. Why did you say yes? You actually had more choices, yeah? 3, 4, 5, 6, 7. Well, let's think about it. What does keep the ball in the pendulum? What does prevent it from rolling back? Friction. Does friction do work to hold it inside it? Does. Did I use any friction? No. The answer is no. My equation is wrong because it doesn't include the work done by friction, which is supposed to be a part of this. Law of conservation mechanical energy says that we should actually include the work done by friction, which cannot be 0. So this is wrong. Now, what is happening? Well, this situation, actually, a very common case when we have 2 problems in one. First, the collision. A bullet is colliding with that pendulum. That is a collision, which we just have learned. And second, after the collision, together they move like a regular pendulum, and that part has nothing to do to collision. That part is related to energy conservation. We've solved the problem about a guy jumping from high level to the low level, but this problem is no different. It's just it's going from low level to high level. So that part is exactly the same. But collision, if we want to use collision, that part correctly, we have to name what kind of a collision is this. We want to use this law. It always works for a collision. But what kind of a collision is that? What do you think? two separate, one whole object traveling together. How do we call it? Yes? Absolutely inelastic. At this point, this slide is just a short memory test. Yes?
Why is that absolutely not?
According to a definition which has been presented. I understand that technically we just have learned it recently, but this is the slide with all definitions. And, and this is the definition. When they travel together, form one object. When they travel together, this collision has a name.
So if it's inelastic, regular inelastic, they can't stick together.
Yes, regular inelastic. It happens, this one, when they keep traveling separately, but some friction work has been done anyway. That's what's actually happening in every natural collision, because there is always some friction. Yes?
Didn't we say that absolutely means that there is no friction with the...
No. No. We said that absolutely, this word might mean two different things. Absolutely inelastic or absolutely elastic, which people now call just elastic, when there is no friction. Friction, no friction. Absolutely inelastic, elastic, which has been called absolutely elastic for many, many years due to good reasons from my point of view. I wouldn't drop that word. So this collision, according to a definition, is absolutely inelastic because they travel together. And now we know everything we need to do. Yeah? We just, well, that's wrong. We just have to follow two-step reasoning. First step, we have to apply to a collision. Second step, we have to apply to energy conservation. That's it. So what's happening before and after the collision? Immediately before and immediately after. 10 grams, 100 meters per second, 990 grams, zero velocity. And after they travel together, 10 plus 990 grams, and the velocity will be, well, who knows what it's going to be? We don't know. And I'm writing a law of conservation of a linear momentum. I know that when I write this law right now, I don't really have to convert grams in kilograms because unit's going to be canceled. But I don't want to confuse you, so I'm going to convert everything in kilograms. Grams. So 1.11 times 100 is 1, 1 plus 0 is 1. So this is now a beginning of a new problem. So it's always, you know, when you solve a previous problem, the solution of the previous problem becomes beginning of a new problem. It's always about solving problems. And in this problem, the law of conservation of mechanical energy now will work. Because now, after the ball is stuck, that's it. When the pendulum swings up, come on. The pendulum, when it's hit, when it swings up, there is no friction, we neglect any resistance. And the only important change happening with the height and the speed. So now, kinetic energy should get transferred into potential energy. So, well, m plus big M v squared over 2 should be equal to m plus big M. The mass of the pendulum doesn't change, times g times h. Turns out, for this part, we actually don't really need to know masses at all, for this part. And to calculate the speed, the height, now we gotta do this, v squared over 2g, and the speed is not 100, the speed is 1. So 1 over 20. Right? So friction actually does a lot of work. It takes a lot of energy from the bullet. Without that, as we saw, the height would have been much, much larger. But we should recognize the importance of what is happening here, the importance of that, the collision. We just cannot relate immediately this and that. We can't do that. We tried, it didn't work. Any questions? Yes?
So where did the friction, where did the impact
Here. When the bullet was entering the box, the pendulum, the parts of the pendulum touching the bullet, touching the ball, made it stop and keep it inside. You could try to make it very, very oily, slippery. In that case, it would just bounce back. And that's what we don't want to have. That's why we want this friction to be strong enough to keep it inside, so they would travel together. This is where friction does work, to keep it. No, unless we would be asked how much work did friction do. Well, we would have to do exactly the same reasoning we did before for the collision. Here, friction does work. And here, there's no friction. All right. So, today, I've got a surprise for you. It's not a surprise test, no. It's a surprise attendance. I do it once in a while, so that's why I finished a little bit earlier. So this is the roster. So please, before you leave, approach the table, find your name, and sign. Doesn't matter where. You don't have to sign 5 times. They're all identical. So you can sign anywhere you want to. 1, 2, 3, 4, 5. And then please feel free to leave. I have my office hour again today from 10 to 11. It's alphabetically, so.
Just waiting for him to give me my exam back if he has it.
So that's why we weren't doing anything with friction. Yeah, you're just fine.
The exam is in my office, so. They're all identical. Your name is exactly at the same place everywhere.